Next, we're going to talk about the CDF, cumulative distribution function. As we have discussed, for the discrete random variable, we have a PMF. And for the continuous random variable, we have a PDF, okay? Which is very inconvenient because we need to talk about the different thing depending on whether random variable is discrete or the continuous. So the question is, can we describe this all kind of random variables, whether it's a discrete or a continuous, with only just a single mathematical concept? If it's possible, then it will be very convenient. That motivates us to define some other function, which is the probability that x is less than or equal to x. That means that for a discrete case, we're going to take a summation over all k such that the k is less than or equal to x. For the continuous, we're going to take an integral from the minus infinity to the x. And that is typically denoted by the large fx, x. So we have defined a new function like fx. This fx is always well defined for the discrete case and the continuous case. Again, because we can always compute the probability for the event for this, right? Whether it is discrete or the continuous, even mixed case. This probability or the function is called the cumulative distribution function because we actually compute the cumulative probability that the x is less than or equal to x. Compared to the cumulative distribution function, in many cases, we are also interested in the probability that x is larger than x, which is equal to 1 minus probability that x is less than or equal to x. And we call this probability complementary CDF, in short, CCDF. So sometimes I'm going to use a CDF, but in most cases, but in some cases, I'm going to use a CCDF if it is necessary. And here's an example of how CDF looks like. Consider this PMF for the discrete case. So here in this case, discrete case. So in this PMF, the probability is defined for the two values like 1 and 2. So the CDF looks like before 1, we have 0 probability because we're talking about this probability. Before 1, we have 0, but at 1, we have to make a jump here in this probability. And also up to the 2, we sustain the same probability, but we have another jump here. And this jump height is equal to the probability that x is equal to 2. And we have a little bit of probability for 3, so this is a little bit of jump. So this is a stepwise constant function for the discrete case. And a similar pattern we can see for this PMF where we have some mass here and another mass here. So up to this point, 0, and then we have a jump here. Let's say this is an A, B, C, A, B, and finally, if we take all summation of this probability should become 1. So finally, we will reach 1 here. For the continuous case, for example, this is the uniform PDF where between the A and B, we have some uniform probability where that uniform probability should be 1 over B minus A. How does the CDF looks like? Well, CDF is what? Again, the probability that x is less than or equal to x. So for example, up to the A point, that value should be 0. But after A, for example, like C, what is the function value of the C in the CDF? That is the area of this thing, right? Because we need to compute the probability that x is less than C. So the area of this guy is this function value. And if you look at this area, when we increase the C to the right direction, then the area should linearly increase. So that's why the function value of the CDF should linearly increase. And finally, we will reach 1. And then after that, it stays at 1. What happens if the PDF is linear function? Then we need to talk about the area of the linear function. So the CDF should become second order function. And also you can easily compute that if this is an x, for example, then the area of this guy should be the function value of this guy, right? This guy. If you compute this area, let's compute that, okay? So let's say this is an h. This area is equal to the x minus a multiplied by h multiplied by 1 over 2. And what is h? H is that this is this value. So b minus a h is equal to b minus a x minus a. So h is b minus a and the 2 square x minus a. Okay, and if we plug in this h to here, and it turns out that b minus a squared, and this is x minus a squared. And that's why we get this. The important thing is that if the PDF is a linear function, the CDF should be quadratic function. We have just tasted how the CDF looks like for an example series of the PMF and the PDF functions. So let's sort of summarize the important CDF properties. First is that it's non-decreasing. Again, why is that? Because we are talking about this probability, and that's the CDF. So it's non-decreasing. And also when x goes to infinity, then this CDF should go to the 1. Whereas if x goes to the minus infinity, the CDF should go to 0. If x is discrete, then the CDF is a piecewise constant function of x, as we have looked at, like this. And the PMF can be obtained by the fxk minus fxk minus 1. And that is the probability x is equal to k. So that means that if once we know the CDF, then we can compute the PMF. Knowledge of the PMF is sort of equal to the knowledge of the CDF. And that's why CDF is a more general concept. If x is continuous, then the CDF function is also a continuous function of x. And also the CDF is an integral from the minus infinity to the x of the CDF. That's why the PDF is a differentiation of the CDF. So that's how the CDF and the PDF is related. Again, that means that if once we know the CDF, then we can reach the knowledge of the PDF or the PMF for the discrete case. Okay, example of using the CDF. So this example is about the distribution of the maximum of the random variable. So here's a scenario. Suppose that we take a test 3 times. We get 3 scores, and your final score will be the maximum of those 3 test scores. Okay? Then my final score, which is random variable x, is maximum of x1 and x2 and x3, where the xi is a test score. And suppose that xi takes a value from the 1 to the 10 uniformly at random with the same probability. So the probability of choosing one value is just 1/10. The question is, what is the PMF of the x? In order to compute the PMF of x, the first approach that one can take is to directly look at the probability of the maximum of 3 things is equal to x. And if you think about this approach 1, it's not that easy, because there are a lot of scenarios where the maximum of x1 and x2 and x3 is the value of x. For example, like, okay, suppose that x1 takes the value x, but x2 is less than x, x3 is less than, or sometimes x3 can be the maximum and so on. So we need to consider a lot of scenarios, which makes solving the problem very difficult. But if we use the CDF, it's actually quite simple. The CDF of x is the probability that the maximum of 3 random variables is less than or equal to x. In order to make the maximum of the 3 random variables is less than x, then we should have the first test score should be less than or equal to x, and the second score and third score. And we know that the xi's are independent here in this case. So it's just a multiplication of 3 things. And the CDF of x1 and x2 and x3 are equal to the x/10. Because it's uniformly random, the probability is 1/10. So less than x is the probability that x1 is less than x is x/10. So it's x/10 to the cube. And then the PMF of the x is just the fx minus fx x minus 1, because this is a discrete random variable. So rather than directly approaching this problem, use the CDF and then PMF. Taking that approach is much simpler.